Hello, my name is Vladyslav Yavtukhovskyi, and I would like to present to you work done by me, Rami, Abukhader, Nils, Tillaeus, and Professor Ning, Xiong in Mellerdalen University on an incremental fuzzy learning approach for online classification of data streams. In recent years, fuzzy systems have achieved widespread application around the globe in many industrial and technical fields, including process modeling, pattern recognition, and automatic control. Many learning methods of fuzzy systems have been developed, whereas they mainly work in batch-based and offline learning manner. A major issue with offline learning is that if one gets a set of new examples in addition to previous ones, it requires starting the whole learning process with all data available. Particularly, offline learning is incapable of handling data streams in an online environment in which fresh data are generated continuously with open ends. This paper is devoted to online learning for data streams classification. We propose a new incremental fuzzy learning approach to modifying an existing fuzzy rule set when a new training example is available without requiring to learn with all examples anew. In recent years, fuzzy systems were widely used for classification and control tasks, with interpretability being the biggest benefit of using it. Incremental fuzzy systems were researched mostly into main areas: reinforcement learning and classification for big data problems. However, both of them have clear limitations. Incremental systems for big data are often not fully incremental. For example, they use full dataset to choose the shape for manage functions of fuzzy sets. It leads to impossibility of using such system for control tasks. And incremental fuzzy systems for control tasks often lacks proper evaluation. First, let's talk about on standard fuzzy rules in classification. Let us consider a pattern classification problem with n-dimensionality of input data and m possible classes. Basically, a fuzzy if-then rule for classification is one of the form that you can see on the slide, where AI1 to AI nth represents a set of antecedent fuzzy sets. Ci is the consequent class of the rule, and W is the weight measuring the confidence of the rule, and big N is the total number of fuzzy rules in the rule set. It should be noted that the ideas of measuring a fuzzy rule with weight and how these weights can affect the final decision as depicted in the following are also valid for other forms of fuzzy classifiers. First, let's briefly mention how standard fuzzy classification is done. Given a new sample with its features represented by x1 to xn, the fuzzy reasoning procedure is as follows. First, we evaluate the firing strength of each rule, T, ETH, and next step is to calculate the voting score for each candidate class C, and we calculate it as beta. Finally, the pattern of the new sample is classified as class C that received the highest voting score. So let's proceed to propose incremental algorithm. First step is that was done is data normalization. For membership function, we use triangle function, and we was chosen with 7 triangles covering interval from 0 to 1 for each dimension. Here you can see those managed functions visualized. One fuzzy set membership functions on the left and all of them put together on the right. Regarding fuzzy rules, we adopt a general premise structure allowing for OR connection of fuzzy sets in rule antecedent. So a fuzzy rule considered for learning in this paper is formulated in the following form, as you can see in the slide. Main benefit of this is that it can cover a group of elementary fuzzy rules that use end connections of single fuzzy sets in the rule premises. A new training example can be considered as positive-negative evidence when it is matched with antecedent of a rule. It provides positive support with which to increase the confidence of the rule if the class of the example is consistent with the consequent rule. Otherwise, it can be considered as counterexample, decreasing the confidence of the rule. This confidence we measure as scores, S plus and S minus. So now let's suppose we have arriving of a new training example E that consists of feature 6 x 1 to xn being the feature values and C as the associated class. Considering the OR connection in the antecedents by firing strengths of the rule, it can be calculated as D on the slide. With the firing strengths calculated above, we can incrementally update the positive and negative scores of rule R by formulas on the bottom left of the screen. And finally, the weight of the rule is calculated based on the updated positive and negative scores. It is also possible to generalize the new training example E into a fuzzy rule to cover the fuzzy region that surrounds it. This fuzzy rule can be created by including the fuzzy sets that receive non-zero membership degrees in the OR connections of the rule antecedent. The rule R dot will then be compared with the existing rule, and if no matching is found, the rule will be added into the rule set, and its weight and positive and negative scores are initialized. Given a new training example, the existing fuzzy rule set can be incrementally updated with the following 3 steps. First is to calculate matching degrees or firing strengths between this new example and each existing rule. And we use matching degrees to update the positive and negative scores of all rules. Second step is to generalize a new training example into a rule and compare this rule with all existing rules. And third, if there is no identical rule in the rule set, then we add this one and initialize weight and scores. So to examine the effectiveness of the proposed incremental method for learning of fuzzy rules, we conducted simulation test on the set of benchmarks datasets taken from UCI machine learning repository. Here are properties of 10 datasets that have been used to evaluate algorithm. In the simulation test for evaluation, we used k-fold cross-validation with k being set to 6. In addition to the rules with a general premise structure, we also built and evaluated the fuzzy rules of the basic form, where end connections of single fuzzy sets were used as rule antecedents. The single fuzzy sets were picked such that they received the highest membership degrees with respect to the individual features of the new training example, as described in Wang-Mendel model. We evaluated the quality of the generated fuzzy sets by applying them to the test data. The classification accuracy on the test data sets were when 50% and 100% of the training examples had been visited. From this table, we can see that learning of rules with general premises can result in higher test accuracy in the mid stage of the learning on 9 out of 10 benchmarks. Since there is no other related work reported concerning online learning of fuzzy rules, our incremental learning method is assessed here in comparison with some other offline learning techniques on the same benchmarks. It can be seen that on 8 out of 10 benchmarks, our algorithm can be competitive and have, or at least have similar performance to offline learning methods. In this work, we have proposed an approach for an incremental learning fuzzy classifiers and have implemented it using Python. The result of our simulation test made on the set of benchmark datasets have shown that our method can acquire quite competitive results compared to some offline learning algorithms. The area of incremental learning of fuzzy classifiers is not well researched, as such future work has a lot of room for development. One interesting direction will be to further enhance the capability of the current incremental learning algorithm and tackle imbalanced data for more complex big data streams. So this is it. Thank you for your attention.